So we know that finite element model we use to have approximate solution. Okay. Now, if you have a simple problem, for example, simple circular beam, cantilever beam, fixed beam, in that case, we can have a exact solution or Poisson solution. But if you have a complicated problem, if you have a complicated geometry, in that case, we may not have our exact solution. Now, to check the accuracy of the FE model, you need to perform some convergence study. So, convergence study basically is that act of coming together. Okay, if the two FE model result, if the result of the two FE model is very close, in that case we can say our model has converged. Okay, so before going to the convergence, here you also have to make sure that other parameter you have modeled accurately. For example, boundary conditions. For example, your material properties. Okay, so material properties in the sense, if you have isotropic material or composite material or orthotropic material or anisotropic material, what type of material you are using, that material model also should be correct. Whether you are using linear analysis or non-linear analysis, that also you have to make sure that you are doing it correctly. Another thing is that the inter-element connections. Okay, if you make sure that inter-element connection. Okay, so if you make sure that other parameter you have modeled correctly, in that case our accuracy of the model will depend upon that elements number, okay, or size of the element or type of the element, what type of element you are using. Okay, so our accuracy or the convergence of a model, FE model, will depend number of element, okay, how many number of element you are using and what type of element you are using. Okay, so if you use certain number of element and certain element type, in that case, if you increase the element number, or if you increase higher order, or if you use higher order element, in that case your result will not change much. Once you achieve that scenario, we can say our FE model has converged. So basically convergence is saying that two consecutive model, okay, giving the same result. Okay, further increase the number of element or further increase that polynomial degree will not change your result. Okay, now here you just see, if we increase the number of element, how we can get our converged solution. Okay, for here, for example, we have exact solution, so here basically we are considering simple problem, for example simple beam plate like that thing, where we can have exact solution and we are using a FE model. Okay, so initially we are using few number of element. If we use few number of element, then our exact result and our FE solution result will vary much. If we increase more number of element, in that case our FE model and our exact solution will come together. Okay, now further increase the number of element. Okay, further increase the number of element will not basically change the result. Okay, further increase the number of element will not change the result. Okay, so here we can say that error which was coming in between our exact solution and FE solution is acceptable. Whatever the error is coming, it is acceptable, and further increase the number of element, that error is not reducing. So here we can say we have achieved our converged solution. Okay, so the convergence basically depends on the two factors. One is that number of element and that type of element or that order of the element. Okay, what is the linear element or quadratic element, that also basically affect the result. So here what we learned, that size of the element and order of the element basically affect the convergence of our finite element model. Okay, and before going to the convergence study, you have to make sure that other modeling parameter is correct. Okay, other modeling parameter, whatever you are assuming, that is correct. We try to understand how element size and degree of polynomial is affecting our result, convergence of our FE model. Here we have one arbitrary shape and we want to find the area. Okay, so one approach is that,
take a rectangular strip, okay, and take that summation of each strip. Okay, you calculate the area of each strip and take the summation of each strip, each rectangular strip. Then you can find the area of this shape. Okay, and the approach is that instead of having rectangular strip, you can take trapezoid. Okay, instead of a straight line like this, okay, horizontal, you can take a trapezoid like things, and you calculate the area of each trapezoid, okay, and take the summation of all the trapezoid, you will get the area of this shape. Okay. Now third approach is that instead of having trapezoid, we can assume some function, some quadratic function or higher function which can capture the shape of this curve, okay, and you take the area of each strip, okay, and take the summation of area all the area of all the strips, you will get that area of what shape. Okay. Now in this approach 1.1, 1.2, 1.3, I hope you will agree that approach 1.3 will give most accurate, because here you can, we are basically here we are making sure that our accuracy of our result depend upon that what type of polynomial we are using. What is a quadratic polynomial or linear or some higher polynomial. Okay. Now second approach is that you take the strip, okay, depending on the width of the strip. If you have larger width, that means if you are using larger size, our accuracy will be less. If you are using smaller strip, in that case our accuracy will be more. So basically, other way we are saying if you are taking more number of element, our accuracy will be more. If you are using lesser element, our accuracy will be less. Okay. So here you have two parameters. One is your polynomial, degree of polynomial, another is your number of element or size. Okay. That is your h. This polynomial also known as the shape functions, because we try to understand how the shape is changing within the element. Okay. Whether it is linearly changed or quadratically changing, depending on that, we have shape functions. And since we use the shape functions to derive our element, for that reason we are saying the linear element, quadratic element, like that. So depending on our degree of polynomial, you are also naming that element of finite element method as a linear element, quadratic element, like that. Okay. This shape function also known as the interpolation function, because we use these shape functions, use this function to interpolate data from one point to another point. For that reason, it is also known as the interpolation functions, that also known as the basis. So basically, shape function has a different name, and since we're using the shape functions to get element, depending on that, we also name the element as a linear element, quadratic element, like that. So here we understand that how our polynomial, degree of polynomial or order of the polynomial, and your size of the element directly affecting our accuracy of that finite element method. Here again, I'm repeating it. You have to make sure that other modeling parameter you have modeled correctly.
Now here we'll see how basically our FE model basically giving convergence results. So here, so we have learned that our FE model basically give converged solution or accuracy of the model depend upon the size of the element and the degree of element. In some cases, you will observe, okay, you will observe that accuracy or convergence basically affecting by that numerical operation, whether we are using reduced integration or full integration, depending on that. Or apart from that, our basically uh, format of that your format of the decimal point, how many decimal point you are using for your calculation, that also will affect our result. Okay. In some cases, you'll observe the thickness, and some cases modeling also affect the result. Okay, that we'll discuss later. But mainly, what we will concentrate that size of the element and that polynomial. Size of the element means h, and the polynomial means p. basically affecting our convergence of a AP model. So here already we have discussed how basically number of element, or you can say the size of element, basically affecting our convergence. Okay. Now thing is that if we keep on increasing your element number, okay, if you're using smaller number of element, okay, smaller element, size element, if you're using smaller size element, in that case our number of element will be more. So if you keep on increasing number of element, in that case our degree of freedom will increase, and the size of the matrix, size of our stiffness matrix, mass matrix also will increase depending on the degree of freedom. Now if you use large number of degree of freedom system, if you use large number of element, so large element also lead to a large number of degree of freedom. In that case our size of the matrix will be very high, and computational time will increase drastically. So basically it will take a lot of time to get one solution, only one single solution. Okay, but on the other hand, okay, on the other hand, you can have a good result. On the other hand, you can have result. Okay, on the other hand, you can have a good result if you use higher order polynomial. Higher order polynomial means we can use, instead of 4 noded element, okay, instead of 4 noded element, you can use 8 noded element. If we have that scenario, you also observe that we are getting good results. So we will see how that size of the element and how order of the polynomial affecting the result. Okay, it may happen that one particular problem you are using 4 noded element. Okay, you are using 4 noded element. In that case, you may have to use 1000 number element. Okay, now if you use 8 noded element, in that case 200 number element may be sufficient to give our converge result. Okay, so now here you can see if you use some higher order element, in that case easily we can get converge solution. Okay, so now here you will see how basically H and P, the size of the element and the polynomial, is affecting our result. So here what happens if we calculate that energy? Okay, if we calculate the energy of our exact model, if we calculate the energy of our AP model, and if we take that difference of the error, difference of the energy, okay, and if you calculate energy norms, if you calculate energy error norms, you will observe the energy error norms, okay, basically depend upon the h to the power p. Energy error norms, okay, will depend, or you can say proportional to the h to the power p. Okay, energy error norms is basically proportional to the h to the power p. So here the energy error norms will be c into h to the power p. Okay, c is basically one factor or proportionally constant or factor that basically affected by that material also. Okay, for example, incompressible material, in that case we have volumetric locking, shell locking. In that case value of c will be very high. Okay, now if the value of c is high, if the value of the c is high, now if you want to have reduced error, if you want to have less amount error, then our h value should be very fine. Okay, in some cases you may be impractical, okay, to use very smaller number of element, but this is one factor you have to take into your account. But this is not that scenario that we are discussing. Very general element and general material. In that case, our error, okay, convergence or error in the energy or convergence, you can say, basically affected by H and the P. And we are also observed that energy error norms basically is depend on that h to the power p, that is proportional to the h to the power p, and that is value basically is equal to c into the h to the power p. Okay, so now why you are calculating energy? Because energy always is to be positive terms, so we will have easy calculations. Okay, and we are calculating energy error norms in averages over the entire domain. Okay, we are calculating energy error, okay, energy over the entire domain, and we are basically calculating the energy error norms. Okay, so in an average sense, and since energy is positive term, so our calculation will be easy and always we will get positive values. Okay, so now if we take the log of it, okay, you'll observe that basically the value, okay, you can take the log of it and plot it. Okay, so in the x-axis basically log of your size of the element, and here if you take the log of your error, okay, you will observe that basically this graph basically slope of the energy error norms basically depend upon that order of the polynomial. Okay, what type of element you are using. Okay, so if you're using linear element, polynomial degree will be 1. If you use a quadratic element, polynomial degree will be 2. Okay, so you can have higher order polynomial also. Now, what happens if you take that order of the polynomial as a 1? In that case, we'll observe that energy or error, okay, error basically reducing in a linear sense with a slope of 1:1. Okay, here you can see the slope basically 1:1. Now, if you use a higher order polynomial, quadratic polynomial, in that case, our error reducing in the ratio of 1:2. If you have cubic order polynomial, okay, if you have cubic polynomial, in that case, our error is reducing 1:3. So here you can see if you use higher order polynomial, okay, if you use higher order polynomial, then error basically error in the energy is reducing the order of degree of polynomial. So if you use higher order polynomial, our error also will reduce drastically. Okay, basically this error is to reduce in a exponential form. Okay, it is basically reduced in exponential form. Okay, exponential ratio. Okay, so now question is that we have agreed that here we have agreed that our h size of the element and the polynomial basically affecting our result. Now question is here that whether is it necessary to have finite mesh for the whole domain, okay, for the whole model. We have agreed that finite mesh will give good result, and if you basically play with degree of polynomial in certain combination, you can have good result. So now once you fixed that, okay, you will use 4-noded element for 4-noded cell element or 8-noded brick element. Okay, if we basically agreed that you use 4-noded cell element or 8-noded brick element, or here you can use 8-noded cell element. Okay, you can use 8-noded cell element or 20-noded brick element. Okay, 20-noded means you have node in between here like this. Okay, so once we decided that you will use 4-noded element or 8-noded brick element or 8-noded cell element or 20-noded brick element, now you have one thing, that fineness of the model. Okay, now question is that whether it is necessary to use finite mesh for the whole domain. Now question, that answer is that no. Okay, that basically depend on that your area of interest. Okay, now thing is that you can use finite mesh for the domain, provided it is taking less time to solve it. Okay, if you're getting the solution in a very lesser time, you can use it. There's nothing wrong with that. Okay, but if you observe that your computational cost is increasing, computational cost is too high. Okay, in that case you can use smaller element in the region of interest. Okay, for example, if you have a plate with a hole or cutout like this, in that case stress concentration will be high here, stress concentration will be here. Okay, so we can use finer mesh in this region. Okay, in this region, but we can use relatively higher mesh, larger mesh in the region which is little bit far away from that hole. Okay, or if you have some complicated geometry, in that case you can use finer mesh in this region, but in the little bit away you can use larger size element. Okay, so basically it depends upon that your area of interest. Okay, otherwise what will happen, your computational cost will increase. Computational cost will increase just like that I already have discussed. Basically our size of the matrix depend on the degree of freedom. If you use a large number of elements, our size of the matrix will be large and our computational cost also will be too much high. Okay, now if you use some trick that wherever your interest is there, wherever there is some chance of stress concentration, you will use finite mesh there, and you can use relatively larger mesh little bit away from that. Okay, that also basically validated by some theory. That theory is basically Stanford principle, which is saying that local stress, okay, stress in one region do not affect the stress of other region. Okay, so this, from this philosophy, okay, also we can validate, or you can basically justify your result that you have used finite mesh in that stress concentration region and you are using little bit larger side in the other domain. okay, other part of that your model. Okay, so I hope you get some idea. Thank you.